What if I told you that the ancient dream of alchemy is alive today, not with magic potions or mythical stones, but with science? What if I told you that inside this pile of discarded dirty gold scrap lies a treasure waiting to be reborn? This isn't about turning lead into gold. This is about taking something already valuable and making it nearly perfect. It's about unlocking the hidden potential trapped within old jewelry, forgotten dental fillings, and discarded electronic components. The process is a quiet one, devoid of roaring furnaces and molten rivers of metal. It happens in a gentle bath of liquid, powered by a force we use every day: electricity. Imagine a transformation so complete that it strips away every impurity, every speck of a lesser metal, leaving only the pure, unblemished soul of gold. This is not a fantasy. It is a repeatable, controllable, and deeply fascinating scientific method. We will embark on a journey that feels like a secret, a piece of knowledge reserved for high-security labs and industrial refineries, but the principles are accessible, and the results are undeniable. What begins as a collection of unwanted, tarnished objects will end as a mound of shimmering, radiant powder, glowing with the unmistakable warmth of pure gold. This essay will guide you through every step of that metamorphosis. We will dismantle the mystique and reveal the elegant simplicity behind the process. You will learn how a simple electrical current can command atoms, compelling them to separate and reorganize. We will observe as copper, silver, and other contaminants are cast aside, falling away like dust. In their place, we will witness the slow, deliberate growth of something extraordinary. This is the story of electrolytic gold refining, a modern alchemist's pursuit of perfection, where knowledge becomes the ultimate catalyst for creating value. The promise is not just about the final product. It is about understanding the very nature of matter and the power we can wield over it. It is about a process that demands patience, precision, and respect for the underlying science. As you follow along, you will see that transforming scrap into 99.99% pure gold is more than just a chemical reaction. It is a testament to human ingenuity. It proves that with the right knowledge, we can bring order from chaos, purity from contamination, and immense value from what others have thrown away. Welcome to the new alchemy. For thousands of years, humanity has purified gold with fire. We have melted it, burned away its impurities, and skimmed the dross from its molten surface. This age-old method, known as fire assaying or cupellation, has served us well. It can produce gold of high purity, often reaching 99.5%. But fire has its limits. It is a brute force method, a blunt instrument in a world that now demands atomic precision. To reach the highest echelons of purity, the kind required for investment-grade bullion and sensitive electronics, we must look beyond the flame. We must turn to a more subtle, more intelligent, and far more powerful force. That force is electricity. Unlike melting, which simply separates materials by their melting points and densities, electrolytic refining operates on a much deeper level. It works atom by atom. The process uses an electrical current to dissolve an impure gold anode into a specially prepared chemical solution, an electrolyte. As the current flows, only the gold ions are selectively drawn through the solution to a cathode. They leave behind the impurities, which either remain undissolved or fall to the bottom of the cell as a sludge. It is a silent, elegant dance of ions, orchestrated by nothing more than a controlled flow of electrons. This method is the secret behind the world's finest gold. When you see a gold bar stamped with the coveted 4 nines, that is, 99.99%, or even 5 nines, it was almost certainly born in an electrolytic cell. This is the process used by the most prestigious mints, professional refineries, and high-tech laboratories across the globe. Why? Because it offers a level of control that fire can never achieve. It allows the refiner to separate gold from other precious metals like platinum and palladium, and to remove even the most stubborn base metals with incredible efficiency. The beauty of this process lies in its quiet precision. There are no dramatic flames, no dangerous fumes from burning alloys, and no complex metallurgical guesswork. Instead, there is only the steady hum of a power supply and the slow, miraculous appearance of pure gold crystals. It is science in its most practical and valuable form. It demonstrates that true power isn't always loud and destructive. Sometimes it is the quiet, invisible force that rearranges the world at an atomic level. This is not magic. It is not an illusion. It is the predictable and profound result of applying fundamental principles of chemistry and physics. This essay is more than just a set of instructions. It is an invitation to witness a profound transformation. We will take you on a complete journey, from a handful of seemingly worthless scrap to a final product of astonishing purity and value. Every stage of the process will be unveiled, demystified, and explained in clear, accessible detail. We will begin with the raw materials, showing you how to identify and prepare your scrap gold to ensure the best possible outcome. Preparation is the foundation of purity, and we will treat it with the importance it deserves, cleaning and readying the metal for its electrochemical rebirth. Next, we will construct our laboratory. You will be introduced to the tools of the modern alchemist: the electrolytic cell, the power supply, the anode and cathode, and the electrolyte solution that makes it all possible. Each component will be explained, not just as an item on a list, but as a crucial player in a scientific drama. We will assemble the cell step by step, turning a collection of simple plastic and metal parts into a powerful engine of purification. You will understand the role of each wire, each connection, and each chemical, building a complete picture of the system before a single volt of electricity is applied. Then, the moment of transformation arrives. We will turn on the power, and you will have a front-row seat to the magic of electrolysis. Through macro lenses and detailed descriptions, you will watch as the impure gold anode slowly dissolves, releasing its treasure into the electrolyte. You will see the impurities fall away, forming a dark sludge at the bottom of the cell, the discarded remnants of a lesser form. Simultaneously, you will witness the breathtaking growth of pure gold on the cathode, as it crystallizes atom by atom into a delicate, shimmering sponge of metal in its most elemental state. Finally, we will complete the journey by harvesting our reward. The process doesn't end when the power is turned off. We will show you how to safely collect the newly formed gold, wash it of any residual chemicals, and dry it into a sparkling powder. The grand finale will be the weighing of the final product, the moment where science translates directly into tangible wealth. From scrap to science, from process to purity, this journey will change the way you see gold. It will empower you with knowledge that has, for centuries, been the exclusive domain of a select few. At its heart, this exploration is about unlocking a code. It is about deciphering the language of chemistry and electricity to command matter to obey our will. The pursuit of 99.99% purity is not just a numerical goal, it is a quest for perfection. It is a standard that separates ordinary bullion from investment-grade assets and industrial-grade material from the high-performance components needed for aerospace and medical technology. Achieving this level of purity elevates gold from a mere commodity to a symbol of ultimate quality and trust. This essay is your key to understanding how that standard is met. This knowledge is powerful. In a world where value is often abstract and fleeting, the ability to create a tangible asset of verifiable purity is a skill of immense significance. It represents a form of self-reliance, a way to add value using intellect and precision rather than speculation. Understanding electrolytic refining is more than a hobbyist's curiosity. It is an insight into the industrial processes that underpin the global economy. This knowledge changes how you view the world around you, revealing the hidden science in the devices we use and the financial systems we trust. It is a lesson in value creation at its most fundamental level. As we proceed, remember that this process must be approached with respect. We are working with electricity and chemicals, forces that are powerful and demand caution. Safety will be a constant theme, a non-negotiable prerequisite for success. But with the proper precautions, the journey is not only safe but also deeply rewarding. It teaches patience as the gold forms slowly over hours. It teaches precision as the slightest variance in voltage or solution can alter the result. It teaches observation as you learn to read the subtle signs of a successful refinement. Prepare to have your perspective shifted. Gold will no longer be just a shiny metal. It will become a substance whose atomic properties you understand and can manipulate. Scrap will no longer be junk. It will be a reservoir of untapped potential. Electricity will no longer be just a utility. It will be a tool for creation. This is your opportunity to learn a process that is both an art and a science, a skill that transforms not only metal, but also your understanding of what is possible. The code to purity is waiting to be unlocked. Let's begin the process. Electrolytic gold refining is a process where, electricity performs a kind of atomic sorting. It's a method of purification that operates at a level so small it's almost impossible to imagine. Unlike melting, which separates metals by heat and density, electrolysis uses a controlled electrical current to separate them by their chemical properties. Think of it as a highly selective dance, where only gold atoms are invited to move across the floor. All other metals, the impurities, are left behind, unable to join the exclusive performance. This process is the pinnacle of precious metal refining, a quiet and elegant technique that delivers, honestly, unparalleled results. At its core, the system is simple. It involves an impure piece of gold, which we call the anode, and a strip of pure material, the cathode. Both are submerged in a special chemical bath known as an electrolyte. When a low-voltage direct current is applied, a remarkable chain of events begins. The impure gold anode starts to dissolve, but not in the way an ice cube melts in water. Instead, it releases its individual gold atoms into the electrolyte solution as positively charged ions. This is the first step in the atomic dance, where gold is liberated from the solid mass it was trapped in. The magic, however, lies in what happens next. The electrical current creates a powerful attraction. The positively charged gold ions, now floating freely in the electrolyte, are drawn irresistibly toward the negatively charged cathode. They travel through the solution on a journey from impurity to purity. Once they reach the cathode, they reclaim their missing electrons, transforming back into pure, solid metal atoms. They plate onto the cathode surface, one by one, building up a crystalline structure of almost perfect gold. It's a slow, methodical, and beautiful process of creation. This method is not just about adding gold to the cathode, it's equally about what it leaves behind. The other metals mixed in with the gold scrap, like copper, silver, zinc, or nickel, react differently to the electrical current and the electrolyte. Some of them might dissolve along with the gold, but honestly, they are not able to complete the journey. Others will not dissolve at all. They simply fall from the dissolving anode and settle at the bottom of the cell. This separation is the secret to the process's incredible effectiveness, leaving only pure gold to complete the transformation. To truly understand this process, you must know the key players involved. First is the anode. The anode is the source material, the hero of our story in its unrefined state. It is a piece of impure gold, often cast into a bar or block from melted scrap jewelry, dental gold, or electronic components. It is connected to the positive terminal of a DC power supply. When the power is turned on, the anode becomes the site of dissolution. It's where the journey begins, as the electrical charge coaxes the gold atoms to let go of their solid form and enter the electrolyte solution as ions. Opposite the anode sits the cathode. The cathode is the destination, the promised land of purity. It is typically a thin sheet of a non-reactive metal, like stainless steel or pure titanium, though a thin strip of pure gold can also be used. The cathode is connected to the negative terminal of the power supply. This negative charge makes it incredibly attractive to the positively charged gold ions moving through the solution. The cathode's job is to be a clean, welcoming surface where the gold ions can land, regain their electrical neutrality, and bond together to form a new, ultra-pure deposit. Between these two electrodes is the most mysterious component, the electrolyte. This is not just any liquid, it's a carefully prepared solution, usually containing gold chloride dissolved in hydrochloric acid. The electrolyte is the medium, the highway upon which the gold ions travel. It must be conductive enough to allow electricity to flow, but also chemically designed to keep the gold ions stable during their journey. The composition of the electrolyte is critical. It ensures that only gold ions are transported efficiently, while helping to suppress the movement of other, less noble metals, thereby maximizing the purity of the final product. Together, these three components, the anode, the cathode, and the electrolyte, form an electrochemical cell. They create a closed circuit where chemistry and electricity work in perfect harmony. The anode gives up its gold, the electrolyte carries it, and the cathode receives it. It's a finely tuned system where each part has a specific and indispensable role. Without any one of these players, the journey of transformation could not happen. They are the essential trinity of electrolytic refining, turning a simple scientific principle into a powerful engine for creating value. The electricity applied to the cell is not just a simple on switch, it's a precise command. The voltage and current are the instructions we give to the atoms, telling them how to behave. By carefully controlling the electrical parameters, a refiner can selectively choose which metal gets to make the journey from the anode to the cathode. This is possible because different metals have different electrochemical potentials. In simple terms, some metals are easier to dissolve and plate than others. Gold, being a noble metal, has a very specific electrical requirement for this process to occur. Imagine you have a dial that controls the power. If you set the voltage too low, nothing will happen. The electrical force is not strong enough to persuade the gold atoms to leave the anode. If you set the voltage too high, you create chaos. You will not only dissolve the gold but also many of the other, less noble metals like copper and nickel. These impurity ions will then flood the electrolyte and may co-deposit on the cathode, contaminating your pure gold. The key is finding the sweet spot, the perfect voltage that is just enough to dissolve the gold, but not high enough to dissolve the other metals. This selective dissolution is the first line of defense against impurities. By keeping the voltage low and the current density controlled, we ensure that the anode releases primarily gold ions into the solution. This is why electrolytic refining is so much more precise than melting. We're not just separating metals based on a physical property like melting point, we're separating them based on their fundamental electrochemical identity. It's like having a password that only gold atoms know, only they are granted access to the electrolyte highway that leads to the pure cathode. Furthermore, the electrolyte itself acts as a second filter. Even if some impurity ions, like silver, manage to enter the solution, the chemistry of the gold chloride electrolyte works against them. For example, any silver ions that dissolve will immediately react with the chloride in the solution to form insoluble silver chloride. This solid material cannot travel to the cathode and simply falls to the bottom of the cell as part of the sludge. This multi-layered system of control, precise voltage and specific chemistry, is what allows the process to systematically strip away contaminants, leaving only the purest gold behind. Professional refineries, national mints, and high-tech industries do not leave purity to chance. For them, gold is not just a beautiful metal, it is a strategic asset and a critical industrial material. When a country's gold reserves are audited or when a microprocessor is bonded with gold wires, the purity must be absolute and verifiable. This is why they overwhelmingly choose electrolytic refining. No other commercially viable process can consistently and affordably achieve the legendary 99.99% purity standard, also known as 4 nines gold. This level of quality is the bedrock of trust in the global precious metals market. Fire refining, while effective for initial purification, simply cannot compete. It hits a wall at around 99.5% purity because some metals, like silver and copper, are very difficult to fully remove through melting alone. Electrolysis, on the other hand, bypasses this problem entirely. It separates gold from these stubborn impurities at the atomic level, achieving a degree of separation that is physically impossible with heat-based methods. This process can even be taken a step further to produce 5 nines, that's 99.999%, or even 6 nines, which is 99.9999% gold, required for the most demanding scientific and technological applications. Another major advantage for professionals is the ability to recover other valuable metals. The sludge that collects at the bottom of the electrolytic cell is not waste. It is often a rich concentrate of other precious metals that were alloyed with the gold, such as silver, platinum, and palladium. This anode slime can be collected and processed separately, turning what would be a loss in a fire refining process into another stream of revenue. This makes electrolytic refining not only more effective but also more economically efficient on a large industrial scale. Every gram of valuable material is accounted for and recovered. Ultimately, the choice comes down to control. The electrolytic process offers an unparalleled level of command over the final product. By monitoring the voltage, current, temperature, and electrolyte composition, refiners can fine-tune the process to achieve predictable and repeatable results day after day. This reliability is non-negotiable for any serious operation. It ensures that every ounce of gold that leaves the refinery meets the exact specifications required by the market. It is this combination of ultimate purity, economic efficiency, and precise control that makes electrolysis the undisputed king of gold refining. When the impure gold anode dissolves, a fascinating separation occurs. Not all metals are treated equally by the electrochemical process. The fate of each impurity depends entirely on its unique chemical properties and its position in the electrochemical series, relative to gold. This selective behavior is the cornerstone of why electrolytic refining is so powerful. We can broadly categorize the impurities into two main groups, those that are less noble than gold, and those that are more noble. Each group follows a different path, ensuring they do not end up on the pure gold cathode. The first group includes the common base metals often alloyed with gold, such as copper, nickel, zinc, and iron. These metals are less noble than gold, meaning they are more reactive and easier to dissolve. However, by carefully controlling the cell's voltage, we can prevent most of them from dissolving in the first place. But even if some of these metals do enter the electrolyte as ions, they are at a disadvantage. The system is optimized for gold. These base metal ions will generally remain in the solution, unable to plate onto the cathode. Over time, they will contaminate the electrolyte, which is why the solution must eventually be managed and replaced. The second group includes metals that are more noble than gold or that react uniquely with the electrolyte. This category includes silver and the platinum group metals: platinum, palladium, rhodium. Silver, for example, might dissolve from the anode, but it immediately encounters the chloride ions in the electrolyte. This causes it to precipitate as silver chloride, a white, insoluble solid that falls to the bottom of the cell. It is chemically blocked from reaching the cathode. The platinum group metals are even more noble than gold, meaning they are harder to dissolve. Under the specific voltage used for gold refining, they will not dissolve at all, simply flaking off the anode and settling in the sludge below. This sludge, known as anode slime, is a valuable byproduct. It is a concentrated mix of all the impurities that did not make the journey: the insoluble silver chloride, the metallic flakes of platinum and palladium, and any other undissolved materials. In a professional setting, this sludge is carefully collected and sent for further processing to recover these other precious metals. This ensures that nothing of value is wasted. The electrolytic cell thus acts as a magnificent sorting machine, directing gold to the cathode, keeping base metals in the solution, and collecting other precious metals in a sludge for later retrieval. Before we take a single step on this journey of transformation, we must build our foundation. This foundation is not made of metal or chemicals. It is made of respect for the power we are about to handle. This process combines two potent forces: electricity and corrosive chemicals. Separately, they demand caution. Together, they command absolute attention and a disciplined approach. Safety is not a suggestion. It is not a footnote in the procedure. It is the very first and most critical step. Without it, the pursuit of gold is not just foolish, it is dangerous. The mindset of safety must be our unwavering guide. Every action you take, from mixing a solution to connecting a wire, must be deliberate and considered. There is no room for haste or shortcuts in this laboratory. The process of refining gold is slow and methodical, and your approach must mirror that. Before you begin, take the time to read through the entire procedure. Understand what you are going to do, why you are doing it, and what the potential hazards are at each stage. This mental preparation is just as important as wearing gloves or goggles. It transforms you from a passive observer into an active, responsible controller of the experiment. This is the professional mindset. Think of your workspace as a sacred ground, a place where science is practiced with reverence. Keep it clean, organized, and free of clutter. A tidy bench is a safe bench. An accidental spill is far less catastrophic when it is contained on a clear surface, rather than soaking into a pile of unrelated papers or tools. Know where your safety equipment is at all times. Your fire extinguisher, your eye wash station, and your first aid kit should be within immediate reach, not buried in a closet. Hope to never use them, but prepare as if you will need them today. This state of readiness is not paranoia. It is professionalism. Finally, never work when you are tired, distracted, or in a rush. The forces at play are unforgiving of carelessness. Electrolytic refining is a process that rewards patience and punishes impatience. If you feel your focus waning, stop. It is better to pause the process and return later with a clear mind than to push forward and make a critical error. Your personal well-being is infinitely more valuable than any amount of gold you could ever produce. Embrace this mindset. Make safety your ritual. Let it be the silent partner in your work, the unseen force that guarantees not only a successful outcome, but also a safe return. In this modern form of alchemy, we don't wear robes, but we do wear armor. This armor is your personal protective equipment, or PPE. It is your first and most intimate line of defense against the hazards of the process. Every piece is essential, designed to protect a specific part of your body from chemical splashes, unexpected electrical arcs, or fumes. Wearing your PPE is a non-negotiable rule. It is the uniform of the serious refiner, a visible commitment to your own safety. Do not even think about handling chemicals or turning on the power supply until you are fully protected. This armor is what stands between you and harm. Your eyes are your most vulnerable and precious asset. A single, tiny splash of the acidic electrolyte solution can cause severe, irreversible damage. For this reason, chemical splash goggles are an absolute requirement. not safety glasses, but fully sealed goggles that protect from splashes coming from any direction, front, side, above, and below. They should fit snugly against your face, creating a barrier that no liquid can breach. Think of them as a window to your work, a window that allows you to see the magic happen while ensuring that the magic can never, ever harm your vision. Protect your sight above all else. Next, we protect our hands and skin. Your hands will be closest to the action, handling beakers, adjusting electrodes, and working with the electrolyte. You must wear chemical-resistant gloves. Nitrile or neoprene gloves are excellent choices, but always check that they are rated for the specific chemicals you are using, primarily hydrochloric acid. It is also wise to wear a long-sleeve shirt and a chemical-resistant apron or lab coat. This protects your arms and body from accidental drips and splashes. Your skin is your body's largest organ. Treat it with the respect it deserves by covering it completely. Finally, we must protect our respiratory system. The electrolyte solution, while not boiling, can still release acidic fumes, especially when the cell is operating. These fumes are corrosive and harmful if inhaled. Therefore, working in a well-ventilated area is crucial, but for maximum safety, a respirator is highly recommended. A half-mask respirator with cartridges rated for acid gas will provide a powerful shield, filtering the air you breathe and ensuring your lungs are protected from invisible hazards. This complete suit of armor, goggles, gloves, apron, and respirator is what allows you to work with confidence, knowing you are shielded from every angle. Electricity is the engine of this entire process. It is the invisible force that commands the atoms, the silent partner that does the heavy lifting. But this power must be tamed and respected. We are working with a DC power supply, and while the voltages are typically low, the potential for danger is always present, especially in a wet environment. Water and electricity are a notoriously hazardous combination. Since our electrolytic cell is, by definition, a container of conductive liquid, we must approach the electrical setup with extreme diligence and a systematic safety-first protocol. Never underestimate the power you are wielding. Your power supply is the heart of the electrical system. Use a modern, regulated DC power supply that allows you to precisely control both voltage and current. These units have built-in safety features, such as short-circuit protection, which can prevent a catastrophe if something goes wrong. Before you ever plug it in, inspect all your wires and connections. Look for any frayed insulation, loose connectors, or exposed metal. Use high-quality wires and alligator clips that create a secure and fully insulated connection between the power supply and the electrodes. A weak or exposed connection is an invitation for a short circuit. The sequence of operations is critical to electrical safety. Always make your connections with the power supply turned off and unplugged. Connect the positive lead to your anode and the negative lead to your cathode first. Double-check that they are secure and that there is no possibility of them accidentally touching each other. Only after everything is connected and you have confirmed your setup is correct should you plug in the power supply. Turn the voltage and current knobs all the way down to 0 before you turn the main power switch on. This ensures there is no sudden surge of electricity. When you are ready to begin the process, slowly increase the voltage to the desired level. Throughout the refining process, keep the area around the power supply and the cell dry and clear. Never touch the electrodes or the electrolyte with your bare hands while the power is on. If you need to make an adjustment, always turn the voltage down to 0 and switch the power supply off first. Following this strict protocol, inspect, connect, check, power on, and power off before touching removes the element of risk and puts you in complete control of the electrical force you are using. Electrolytic refining uses powerful hazardous chemicals, especially gold chloride and hydrochloric acid. Proper ventilation is essential. Always use a fume hood or, at minimum, a strong cross breeze with fans to direct fumes outside. Never work in closed spaces. Acid vapors are invisible but dangerous. Always add acid to water, not the reverse. and use only glass or acid-resistant plastic containers, clearly labeled and never repurposed from food use. Keep baking soda nearby to neutralize spills, and store acids in sealed, ventilated cabinets. Dispose of used solutions as hazardous waste, following local regulations. Responsible science means responsible cleanup. The DC power supply is the heart of electrolytic refining, providing precise control over voltage and current. Use a regulated bench power supply with variable voltage and current and clear digital displays. Connect with quality copper wires and insulated alligator clips. Red to anode, black to cathode. Monitor the process closely. Stable readings mean smooth refining, while fluctuations signal issues. The power supply is your conductor's baton. Master it for pure results. Precision here is the difference between success and failure. The electrolytic cell is where impure gold transforms into pure gold. Use a glass or acid-resistant plastic container, never metal. Suspend your impure gold anode and a stainless steel or titanium cathode parallel, never touching, with space for electrolyte flow. Use a non-conductive support and, for the anode, a porous polypropylene bag to catch debris. The anode dissolves, releasing gold ions. The cathode collects pure gold. This setup is simple, but every detail matters for purity. The electrolyte, a mix of gold chloride, distilled water, and hydrochloric acid, is the medium for gold's journey. Always use distilled water. Tap water introduces impurities. Add acid to water, then gold chloride, following safety protocols. The solution's concentration is critical. Too weak, and refining is slow. Too strong, and unwanted metals dissolve. Over time, contaminants build up. Replace or process the solution as needed. The electrolyte's health directly affects your gold's purity. Precision and safety require the right tools. Use a digital scale and 0.001 G accuracy to measure gold before and after refining. Stock glass beakers, stirring rods, and plastic funnels for safe handling. Rinse gold only with distilled water to avoid recontamination. Keep baking soda, a spill kit, and an eye wash station on hand. Safety is non-negotiable. These accessories turn your workspace into a controlled, professional lab. Preparation is the foundation of pure gold refining. Clean your gold scrap thoroughly. Remove dirt, stones, and non-metallics. A clean anode dissolves evenly, keeps the electrolyte healthy, and ensures a purer final product. Good prep means less waste, more efficiency, and better results. Invest time. Here, it pays off in purity and yield. Let's start by preparing our raw material for its transformation. The first task in preparation is to know what you are working with. Gold scrap comes in countless forms, from old family heirlooms to discarded electronic components. Each piece tells a story, not just of its past life, but of its metallic composition. Your job is to become a detective, examining each item to understand its potential. Start by spreading out all your scrap on a clean, well-lit surface. This is your treasure map. Your goal is to sort it into categories based on its likely purity and composition. This initial sort will inform how you treat each piece moving forward. Look for the carat stamps. In jewelry, these small markings are your best initial clue. A piece marked 14K is 14 parts gold out of 24, or 58.3% gold. A piece marked 10K is 41.7% gold, while 18K is 75% gold. Group your items by their carat value. This is important because lower carat gold contains a higher percentage of other metals like copper, silver, and zinc. These alloys might require special consideration later in the process. Also, Be on the lookout for markings like GF, gold-filled, or HGE, heavy gold electroplate. These items have only a very thin layer of gold over a base metal core, and are generally not suitable for this type of refining. Beyond jewelry, you might have dental gold, which is often a high-carat alloy designed for durability, or electronic scrap, like CPU pins and connectors. Electronic scrap is typically high-purity gold, but it is plated in extremely thin layers over other metals. Processing e-scrap to create an anode requires a different chemical pre-processing path to strip the gold first, and is a complex topic on its own. For now, we will focus on solid gold alloys found in jewelry and similar items. Separate any items that are clearly not gold, or are heavily plated. Your goal is to create a pile of solid gold alloy items that you can confidently work with. This sorting phase is also your chance to perform a preliminary inspection for non-metallic attachments. Are there diamonds or other gemstones set in the rings? Are there bits of enamel or plastic decorations? Make a separate pile for items that will require significant mechanical cleaning. This simple act of sorting transforms a chaotic pile of scrap into an organized inventory. It gives you a clear picture of your starting assets and allows you to create a more homogeneous batch of metal for your anode. A consistent starting alloy leads to a more stable and predictable refining process. This is the first step in taking control. Once your gold scrap is sorted, the physical work of cleaning begins. This stage is focused on removing everything that is not metal. Every speck of dirt, every trace of oil from human skin, and every decorative stone is an impurity that must be removed. Start with the most obvious offenders. Gemstones. Many people are tempted to leave small stones in, thinking they will burn away or fall off. This is a mistake. They will contaminate your process. Using a small pair of pliers or a jeweler's prong pusher, carefully remove any and all stones from their settings. Place them aside. They are not part of this journey. Next, attack the grime. Years of wear can leave a thick layer of dirt, soap scum, and oils packed into the crevices of old jewelry. This needs to go. A simple but effective method is to use an ultrasonic cleaner. These devices use high-frequency sound waves to create microscopic bubbles in a cleaning solution, which blast away dirt from even the tiniest corners. A bath in an ultrasonic cleaner with a bit of ammonia-based cleaning solution can work wonders, revealing the bright metal hidden underneath a layer of grime. If you don't have an ultrasonic cleaner, a stiff brush, hot water, and a strong detergent will also work. It just requires more manual effort. After the bulk of the dirt is gone, inspect each piece again. Look for any remaining non-metallic elements. Things like enamel inlays, remnants of watch bands, or any plastic or epoxy fillers must be physically removed. This can sometimes require a small file, a sharp pick, or even a rotary tool with a small grinding bit. The goal is absolute metallic purity. You want to be left with nothing but the gold alloy itself. Every bit of foreign material you remove at this stage is one less contaminant your electrolytic cell has to deal with. This is meticulous, detailed work, but your patience will be rewarded. The final step of the mechanical clean is a thorough rinse. After brushing, scrubbing, or ultrasonic cleaning, you must wash away any residual cleaning agents. Rinse each piece thoroughly, first under hot tap water, and then finish with a final rinse in distilled water. The distilled water rinse ensures that no chlorine or mineral deposits from your tap water are left on the surface of the metal. Once rinsed, lay the clean, bare metal pieces out on a clean towel and allow them to dry completely. What you are left with now is a pile of clean, pure alloy, ready for the next stage of its transformation. Sometimes, your gold scrap may have a very high purity, such as 22 karat or 24 karat scrap, or it might be a low purity alloy with very little silver. While this sounds like a good thing, it can actually cause a problem in the electrolytic cell known as passivation. This happens when a thin, non-conductive layer forms on the surface of the anode, stopping the flow of electricity and halting the refining process. This layer is often caused by the formation of insoluble gold chlorides when there isn't enough other metal, like silver and copper, to help the anode dissolve evenly. To prevent this, we use a classic metallurgical technique called inquartation. Inquartation is the process of intentionally alloying your gold with other metals, primarily copper and silver, to bring the gold content down to around 25% or 1/4 of the total mass, hence the name inquartation. By doing this, you ensure there's enough base metal in the anode to allow it to dissolve smoothly and completely in the electrolytic cell. It also serves another critical purpose. If your gold alloy contains platinum group metals, inquartation helps to liberate them so they can fall into the anode sludge as the anode dissolves, rather than getting trapped in the passivated surface. To inquart your gold, you will need to melt it. This requires a furnace or a torch capable of reaching the melting point of gold, 1064 degrees Celsius, or 1948 degrees Fahrenheit, and a graphite or ceramic crucible. You will place your clean gold scrap into the crucible, along with a calculated amount of pure copper and, if possible, silver. The ideal ratio to aim for is roughly 3 parts silver or copper to 1 part gold. You heat the crucible until all the metals are molten and form a single, homogeneous, liquid alloy. Gently swirling the crucible ensures a thorough mix. This step must be done with extreme caution, wearing proper heat-resistant personal protective equipment. Once the metals are fully alloyed, you will pour the molten metal into a container of cold water. This process, called granulation, causes the metal to instantly solidify into small, popcorn-like shots or grains. This dramatically increases the surface area of the alloy. While you can cast the inquarted metal into an anode bar, granulating it offers an alternative. These small grains can be packed into a special titanium basket that serves as the anode. This high surface area further aids in a smooth and efficient dissolution in the electrolytic cell, making it a preferred method for many professional refiners. This seemingly counterintuitive step of adding impurities is a powerful secret to achieving the purest possible result. The moment has arrived to construct the very heart of our operation, the electrolytic cell. This is where the quiet miracle of atomic separation will occur. But before we assemble the components, we must first stage the arena. Your workspace is more than just a table. It is your laboratory, and it must be prepared with the same precision and respect you give to the process itself. Begin by clearing a dedicated area. This space should be stable, level, and free from any clutter or flammable materials. A clean, organized surface is the foundation of a safe and controlled experiment, preventing accidents and allowing for clear, focused work. Once your surface is clear, create a layer of secondary containment. This is a simple but critical safety measure. Place your electrolytic cell, the glass beaker or plastic container, inside a larger shallow tray made of chemical-resistant plastic. This tray acts as a moat. In the unlikely event of a crack, leak, or spill from your primary cell, the tray will capture the corrosive electrolyte, preventing it from spreading across your workbench and onto the floor. This small step can turn a potential disaster into a minor, manageable incident. It is a hallmark of professional practice and a testament to a safety-first mindset. Now, arrange your tools and materials in a logical, accessible order around your workspace. Place your direct current power supply off to one side, ensuring its ventilation ports are unobstructed and it is away from the immediate area where liquids will be handled. Keep your distilled water, beakers for rinsing, and your neutralizing agent, baking soda, within easy reach. The anode and cathode should be laid out on a clean cloth, ready for installation. By creating this organized layout, you establish a workflow. You will know where everything is without having to search, minimizing movement and reducing the chance of bumping or spilling anything once the cell is live. Finally, consider your ventilation. This is a crucial part of preparing your workspace. Even before the electrolyte is introduced, ensure your ventilation system is active. If you are using a fume hood, turn it on. If you are using fans for cross-ventilation, position them correctly to pull air away from your position and direct it outside. The environment must be prepared to handle the chemical fumes before they are even generated. Staging your arena is a ritual of preparation. It is the act of creating a controlled environment where science can be performed safely and effectively, setting the stage for the transformation that is about to begin. With the stage set, we now bring in the two main actors, the anode and the cathode. These are the pillars of the electrolytic cell, the origin and destination of our gold. The installation must be done with care, ensuring they are positioned correctly for optimal performance. The distance and orientation between them directly impact the flow of electricity and the quality of the gold deposit. First, take your anode, the bar of impure gold you have prepared. If you are using an anode bag, carefully place the gold bar inside it now. This porous bag will act as a filter, catching the invaluable sludge as the anode dissolves. Next, you will suspend the anode in the cell. Using a non-conductive support rod, a piece of wood or heavy plastic laid across the top of the beaker works well. Hang the anode so that it is submerged in the center of the cell. It should not touch the bottom or the sides of the container. The top of the anode should have a secure point of connection, often a wire or hook cast into the bar, which will be used to both hang it and connect it to the power supply. Ensure it hangs straight and is stable. This anode is the source of our wealth, and its position marks the starting line for the gold's journey. Now, introduce the cathode. This is the thin sheet of stainless steel or titanium that will collect the pure gold. The cathode must be placed parallel to the anode, like two walls facing each other. The distance between them is critical. A general rule of thumb is to maintain a gap of about 1 to 2 inches. If they are too close, you risk a short circuit. If they are too far apart, the electrical resistance of the electrolyte increases, making the process less efficient. Hang the cathode from your support rod, ensuring it is parallel to the anode, and most importantly, that there is no possibility of them touching. This parallel arrangement is crucial for creating an even electrical field. An even field encourages the gold to deposit smoothly and uniformly across the entire surface of the cathode. If the electrodes are angled or crooked, the current will concentrate in the areas where they are closest, leading to uneven growth and potentially lower purity deposits. Take your time with this step. Adjust the positions until you have two perfectly parallel pillars standing within your cell, separated by a carefully measured gap. This precise geometry is the framework upon which a successful refinement is built. The cell is assembled, the pillars are in place, but the space between them is empty. It is time to introduce the lifeblood of the process, the medium that will carry the gold from its impure past to its pure future. It is time to add the electrolyte. This step must be performed with the utmost care, wearing your full personal protective equipment. Goggles, gloves, and respirator are mandatory. The electrolyte is a corrosive acidic solution and must be handled with deliberate, steady movements. There is no room for error or splashes when working with this potent chemical solution. Using a clean glass or plastic beaker with a pouring spout, carefully measure out the required amount of electrolyte. You need enough solution to submerge the majority of the anode and cathode, but not so much that it risks splashing out of the cell. The liquid level should remain well below the rim of your beaker. Slowly and gently, pour the electrolyte into the electrolytic cell. Pour it down the side of the beaker to avoid splashing and to minimize agitation. Watch as the clear, often yellow-tinted liquid fills the space around the electrodes, bringing the cell to life. As you pour, observe the liquid level. Ensure that the active surfaces of both the anode and cathode are fully submerged. The portion of the electrodes that is above the liquid will not participate in the reaction. Critically, ensure that the electrical connection points at the top of the anode and cathode remain well above the surface of the electrolyte. If the electrolyte touches the alligator clips or connection wires, it will cause them to corrode rapidly and will interfere with the electrical circuit, potentially stopping the process altogether. The separation between the wet and dry zones must be distinct and absolute. Once the electrolyte is in, take a moment to pause and inspect the cell. Look at it from all sides. Are the anode and cathode still parallel and properly spaced? Is the liquid level correct? Are there any leaks? This is your final opportunity to make any physical adjustments before electricity is introduced. The cell is now a complete, self-contained chemical system. It is a battery in reverse, waiting for an external command. The stage is fully set, the actors are in place, and the medium for their interaction is present. The system is armed and ready. The cell is built, filled, and waiting. Now we must give it the command to begin. We will do this by connecting it to the power supply, completing the circuit that will drive the transformation. This step bridges the gap between the chemical world and the electrical world. Approach this task with a methodical, safety-first sequence. Your DC power supply must be switched off, and the voltage and current control knobs must be turned all the way down to 0. This ensures that no electricity can flow accidentally while you're making the connections. Take the red wire, the positive lead, from your power supply. Using the alligator clip at its end, firmly attach it to the connection point at the top of the anode, the impure gold bar. Ensure the clip has a strong grip and is making good metal-to-metal contact. The connection should be secure and well clear of the electrolyte solution. This positive connection is what will give the anode the electrical charge it needs to begin dissolving, releasing its gold ions into the solution. The path for dissolution is now established. Next, take the black wire, the negative lead. Attach its alligator clip to the connection point on your cathode, the stainless steel or titanium plate. Again, ensure the connection is firm, secure, and far away from the corrosive liquid. This negative connection is what will create the powerful attraction for the positively charged gold ions, drawing them out of the solution and onto the cathode's surface. With this connection, the destination for purity is now electrically active and ready to receive. You have just wired a complete circuit for creation. Double-check everything. The red positive lead goes to the anode, the impure gold. The black negative lead goes to the cathode, the pure collector plate. The connections are tight. The clips are not touching each other or anything else that could cause a short circuit. The power supply is still off. This simple two-wire connection is the final piece of the physical setup. The entire system, a carefully constructed assembly of plastic, metal, and liquid, is now linked to its power source, poised on the edge of action. The silent machinery of purification is fully assembled and awaiting its first spark of life. Before you breathe life into the cell, you must perform one last ritual, the final check. This is not a step to be rushed. It is a deliberate, systematic review of your entire setup, a moment of pause to ensure every detail is correct before you commit to the process. This protocol is your last defense against error and your final confirmation of readiness. Think of yourself as a pilot performing a pre-flight checklist. The journey ahead is long and requires a perfect takeoff. Begin by visually inspecting the entire cell one more time, looking through the transparent walls of your container. Confirm the geometry. Are the anode and cathode still perfectly parallel? Has anything shifted while you were making the connections? A stable geometry is key to a stable process. Check the spacing. Ensure the gap is sufficient to prevent any accidental contact. Look at the electrolyte level. Is it high enough to cover the working surfaces but low enough to be safe? Scan the surrounding area. Is your workspace still clean and organized? Is your neutralizing agent within immediate reach? This visual sweep confirms the physical integrity of your setup. It is the first layer of your final check. Next, review your electrical connections with intense focus. Trace the wires with your eyes. Follow the red wire from the positive terminal of the power supply to the anode. Follow the black wire from the negative terminal to the cathode. Verbally confirm the connections out loud. Positive to anode, negative to cathode. This simple act of verbal confirmation engages another part of your brain and can help catch a mistake you might otherwise overlook. Confirm that the power supply's main switch is in the off position and that the voltage and current dials are at 0. This electrical review is non-negotiable. Finally, check yourself. Is your personal protective equipment properly fitted? Are your goggles secure? Is your respirator sealed? Are your gloves intact? You are part of the system and your safety is the most important component. Take a deep breath. You have prepared your materials, staged the arena, built the cell, and confirmed every connection. You have followed the protocols of the professional. The system is ready. The science is ready. You are ready. This final methodical check transforms hope into confidence. You are not just starting a chemical reaction, you are initiating a controlled, predictable, and safe process of purification. The moment of truth has arrived. Every stage of preparation, every safety check, and every carefully assembled component has led to this single point in time. The cell stands ready, a silent and motionless vessel of potential. With your full personal protective equipment securely in place, you reach for the power supply. This is the first spark of life, the command that will awaken the atomic forces within the cell. With the voltage and current dials still set to 0, you press the main power switch to the on position. The digital displays light up, but the cell remains unchanged. The system is live, but the process has not yet begun. Now, with a slow and steady hand, you begin to turn the voltage knob. You are not just turning a dial. You are gradually increasing the electrical pressure within the system. As you inch the voltage up from 0, 0.1 volts, 0.2 volts, 0.3 volts, you watch the cell with intense focus. At first nothing happens, but as you approach a specific threshold, typically between 0.8 volts and 1.2 volts for a gold chloride electrolyte, the magic begins. You will see the first sign of life. The ammeter on your power supply, which measures the flow of current, will begin to register a reading. This is the signal that the circuit is complete and that electrons have begun to flow. The atomic migration has been initiated. Simultaneously, you may observe the first visible changes within the cell itself. Look closely at the cathode, the plate of pure stainless steel or titanium. You might see a fine stream of tiny bubbles beginning to form on its surface. This is often hydrogen gas, a harmless byproduct of the reaction, signaling that the cathode is electrically active and ready to receive. Then, shift your gaze to the anode, the bar of impure gold. The liquid immediately surrounding it may begin to shimmer or develop a slightly darker, more concentrated color as the very first gold ions dissolve into the electrolyte. This is the quiet, subtle beginning of an immense transformation. You have provided the spark. The electrical command has been given, and the atoms have begun to obey. The anode has started its slow sacrifice, and the cathode is preparing for its reward. From this moment forward, the process will continue on its own, governed by the laws of electrochemistry and the parameters you have set. You are no longer an assembler of parts. You are now the guardian of the process, an observer of a slow and beautiful dance. The silent, invisible force of electricity is now actively sorting matter, atom by atom, right before your eyes. The magic has officially begun. Your attention is now drawn to the anode, the source of our treasure. This is where the most dramatic dissolution occurs. As the minutes turn into hours, you will witness the slow, methodical erosion of the impure gold bar. It does not melt or bubble away aggressively. Instead, it appears to simply and silently vanish into the solution. The surface of the anode, which may have been cast with a smooth finish, will begin to look etched and pitted. The electrical current is selectively plucking gold atoms from its surface, releasing them as ions into the electrolyte, leaving the less noble and more noble impurities behind to face their own fate. As the gold dissolves, the other metals alloyed with it are exposed. The anode begins to change color. If it contains a high amount of copper, you will see a greenish tint develop in the electrolyte immediately surrounding it, as some copper ions inevitably enter the solution. More dramatically, the surface of the anode itself may become coated in a dark, murky layer. This is the visible accumulation of impurities that cannot dissolve under the controlled voltage you have set. This dark coating consists of the more noble metals, like platinum and, most significantly, the silver chloride that forms instantly when any silver dissolves. This dark layer of impurities does not stick to the anode forever. As the gold dissolves from underneath it, these materials lose their purchase and flake off. They fall away from the anode, drifting slowly downwards. This is why the anode bag is so crucial. It acts as a net, catching this dark, valuable sludge and preventing it from floating through the cell and contaminating the cathode. Watching the anode bag slowly darken and fill with this anode slime is a deeply satisfying sight. It is the physical evidence of purification, the literal separation of the valuable from the invaluable, the pure from the impure. Over the full course of the refinement, which can take many hours or even days depending on the size of the anode, you will watch it shrink. It is a process of sacrifice. The anode gives up its substance, its very form, so that its purest essence can be reborn elsewhere. Its sharp edges will round off, holes may appear, and eventually, it will be completely consumed, leaving behind only the rich, dark sludge in the bag. This gradual disappearance is a powerful visual metaphor for the refining process itself. For purity to be created, the impure form must be completely and utterly deconstructed. While the anode is making its sacrifice, a quiet miracle is happening on the other side of the cell. Shift your focus to the cathode, the clean plate of stainless steel or titanium. This is the site of creation, the destination for the gold ions that have successfully completed their journey across the electrolyte. At first, the change is almost imperceptible. The smooth metallic surface of the cathode may take on a slightly hazy or discolored appearance. This is the very first layer of gold, just a few atoms thick, bonding to the surface. It is the seed from which a great treasure will grow. As time progresses, this initial haze will blossom into something extraordinary. You will begin to see the distinct formation of a solid deposit. This is not a smooth, mirror-like plating. The gold deposited through electrolysis at these low voltages grows in a unique, crystalline form. It often appears as a soft, brownish or mustard-colored sponge. Under a magnifying glass you can see the intricate dendritic structures, tiny branching tree-like crystals of pure metal. This is gold in one of its most elemental and beautiful forms, a delicate lattice built atom by atom. The growth is slow, but relentless. The deposit will become thicker and more substantial as the hours pass. It will grow outwards from the cathode, a strange and beautiful coral reef of pure gold. The color may vary depending on the specific conditions in your cell, but it will have a characteristic soft, earthy texture. It is crucial that this growth remains undisturbed. Any agitation of the cell could cause pieces of this delicate deposit to break off and fall to the bottom. The goal is to let it grow as a single, coherent mass, clinging to the cathode from which it was born. This is the reward for your patience and precision. Every crystal you see forming is a testament to the process working correctly. It is the physical manifestation of purity. While the anode was a chaotic mix of different metals, the cathode is a sanctuary for only one. The electrical and chemical filters you have put in place have ensured that only gold ions are allowed to complete the journey and plate onto this surface. You are watching wealth being created not by fire or by force, but by the quiet, intelligent, and elegant laws of science. This is the birth of 99.99% pure gold. Once the process is underway, your role shifts from an active participant to a vigilant observer. The electrolytic cell will communicate its health and progress to you through a series of subtle signs. Learning to read these signs is the key to maintaining a successful refinement and troubleshooting any problems that may arise. Your most important diagnostic tools are the digital displays on your DC power supply. The voltage and, more importantly, the amperage readings tell a continuous story about what is happening inside the cell. A steady, stable amperage reading is the sign of a healthy, efficient process. Let's say you set your voltage to 1.0 volts and the current stabilizes at 2.5 amps. This becomes your baseline. If you notice the amperage beginning to slowly drop over time, it could be an early warning sign. A falling current at a constant voltage indicates that the electrical resistance in the cell is increasing. This might be caused by the anode passivating, where a non-conductive layer is forming on its surface and preventing dissolution. It could also mean that the electrolyte is becoming depleted of gold ions or overly contaminated with other metals. A slight, gentle agitation of the electrolyte or a very small increase in voltage might help, but significant drops require careful diagnosis. Conversely, a sudden spike in amperage is a major red flag. If the current jumps to a very high number and the power supply's overload protection kicks in, it almost always means you have a short circuit. This is a dangerous situation that must be addressed immediately by turning off the power. A short circuit typically happens if the growing gold deposit on the cathode has reached across the gap and touched the anode bag, or if a piece of metal has fallen and created a bridge between the two electrodes. This is why maintaining the correct distance and ensuring the cell remains undisturbed is so critical. Beyond the electrical readings, use your eyes. Observe the color of the electrolyte. A healthy gold chloride solution should remain a relatively clear, yellowish green. If it starts to turn a deep dark blue or green, it is a sign that a large amount of copper is dissolving into the solution, which could indicate your voltage is set too high. Look at the deposit on the cathode. It should be that characteristic soft, brownish yellow. If it starts to appear dark, slimy, or discolored, it may be a sign that impurities are co-depositing, and your parameters need adjustment. By constantly monitoring these visual and electrical cues, you can guide the process to a pure and successful conclusion. The magic of electrolysis is not the magic of a sudden spectacle. It is the magic of a slow, deliberate, and patient transformation. In our world of instant gratification, gold refining teaches a valuable lesson. Some of the most profound and valuable creations take time. The journey of each gold ion from the impure anode to the pure cathode is a solitary one, and millions upon millions of these individual journeys must take place to build a visible deposit. This is a process that cannot be rushed. Attempting to speed it up by cranking up the voltage will only lead to chaos and contamination. The rate of deposition is governed by Faraday's laws of electrolysis, which directly link the amount of metal deposited to the total electrical charge passed through the cell, current multiplied by time. This means that to produce a significant amount of gold, you need to run the cell for a significant amount of time. A small hobby-scale cell might run for 12 to 24 hours to process a few ounces of gold. Large industrial cells run continuously for days or even weeks. You must embrace this timeline, set up your cell, initiate the process, and then trust it to do its work. This period of waiting is not passive, it is an active state of observation. It is a time to check in on the cell periodically, monitoring its vital signs, the voltage, the amperage, the color of the solution, the growth on the cathode. It is a time to ensure the environment remains safe and controlled. This slow dance of atoms teaches a form of mindfulness, a focused attention on a gradual process. It is a stark contrast to the violent, fiery drama of melting gold with a torch. This is a quiet, intellectual, and controlled creation, and it demands a calm and patient operator. Ultimately, patience is rewarded. The longer you allow the cell to run correctly, the more of the anode will be consumed, and the thicker the deposit of pure gold on the cathode will become. Resisting the temptation to stop the process early to check on your treasure is part of the discipline. You must let the science run its course. This extended passage of time is what allows for the profound degree of separation to occur, ensuring that only the purest gold completes the journey. In the quiet hum of the power supply and the slow growth of the crystals, you will find that the truest magic of this process is found in its deliberate, unhurried, and perfect pace. After hours, or perhaps even days, of patient observation, the time has come to reap what you have sown. The anode has shrunk to a fraction of its original size, or disappeared completely, and the cathode is heavy with a thick, beautiful deposit of crystalline gold. The harvest is the moment you physically claim your reward, transitioning from a passive observer to an active participant once more. This process must be done with the same methodical care as the setup. The first step, before touching anything, is to safely power down the entire system. Turn the voltage and current knobs on your power supply all the way back down to zero, then switch the main power off. With the electrical circuit now dead, you can safely disconnect the alligator clips from the anode and cathode. Handle them with care as they may have some residual chemical fumes on them. Now, it is time to remove the electrodes from the electrolyte. Very slowly and carefully, lift the support rod holding the cathode out of the cell. The deposit of pure gold is incredibly delicate and spongy. Any sudden movements could cause it to break apart and fall into the electrolyte below. Let any excess electrolyte drip back into the cell for a few moments, then immediately transfer the cathode and its precious coating to a clean beaker filled with distilled water. Next, you will retrieve the anode bag. Just like with the cathode, lift it out of the solution slowly, allowing the electrolyte trapped inside to drain back into the cell. This bag contains the valuable anode sludge, a concentrated mix of silver, platinum group metals, and other undissolved impurities. Do not discard it. Place the entire bag into its own separate, clearly labeled beaker for later processing. Recovering the values from this sludge is a separate refining process, but an important one for any serious refiner. For now, our focus remains on the pure gold we have just harvested from the cathode. Finally, with the electrodes removed, your electrolytic cell now contains the used electrolyte. This solution is still corrosive, and now contains dissolved base metals, like copper. It should be covered and stored safely for future processing or proper neutralization and disposal according to local regulations. The arena is now cleared, and all that remains is to process our prize. The cathode, sitting in its first bath of distilled water, holds the culmination of our efforts. The harvest is complete, but the final purification and verification are yet to come. This is the transition from creation to collection. The gold you have harvested from the cathode, while incredibly pure in its metallic form, is currently saturated with the corrosive electrolyte solution. If left as is, the residual acid would not only be a safety hazard, but would also add false weight and could slowly react with the gold over time. To achieve true, clean 99.99% purity, we must perform a cleansing ritual. This involves a series of thorough washes with pure distilled water. This step is non-negotiable and must be done with meticulous attention to detail. The goal is to remove every last trace of the chemical solution, leaving behind nothing but pure gold. Begin by gently scraping the soft, spongy gold deposit from the cathode plate into the beaker of distilled water you placed it in. The gold should come off easily. You can use a plastic scraper or a glass stirring rod to gently nudge it from the surface. Avoid using metal tools that could scratch and contaminate your pure product. Once all the gold is in the beaker, swirl it gently. You will see the water become cloudy with the displaced electrolyte. Let the heavy gold powder settle completely to the bottom of the beaker, which should only take a few moments. Once the gold has settled, carefully pour off, or decant, the rinse water into a separate waste container. Be very careful not to pour out any of the fine gold particles, along with the water. This is a moment that demands a steady hand. After decanting the first rinse, add fresh distilled water to the beaker, swirl again, let it settle, and decant again. You must repeat this process multiple times. How many times? Until the water you pour off is perfectly clear and has no trace of the yellowish-green tint from the electrolyte. A good rule of thumb is to wash it at least 5 to 7 times. For the final washes, it is good practice to use a pH test strip to check the rinse water. Dip a strip into the water after you have swirled it with the gold. A truly neutral rinse, free of any residual acid, will show a neutral pH of 7. This is your scientific confirmation that the cleansing ritual is complete. This obsessive washing might seem repetitive, but it is the only way to guarantee that the final product you weigh is nothing but pure, unadulterated gold. You're not just cleaning the gold, you are finalizing its purity. Your gold is now metallurgically pure and chemically clean, but it sits as a wet, heavy sludge at the bottom of a beaker. To transform it into the final, beautiful, and weighable form of a shimmering powder, it must be completely dried. Any residual moisture will add significant weight, giving you an inaccurate and disappointing final measurement. The drying process must be gentle to avoid blowing away any of the fine, lightweight powder. The simplest and safest method is to use a low, even heat source. A laboratory hot plate set to a low temperature or even a simple electric food warmer can work perfectly for this task. First, decant as much of the final rinse water as possible from your beaker without losing any gold. You want to start with a wet paste rather than a slurry. Place the beaker containing the wet gold powder onto your heating surface. It is often best to transfer the gold from the beaker to a wider, shallow glass dish, like a Pyrex or borosilicate evaporating dish. This spreads the powder out into a thinner layer, which dramatically increases the surface area and allows it to dry much more quickly and evenly. This also reduces the risk of the powder clumping together. As the heat gently warms the dish, the remaining water will begin to evaporate. You will see steam rising from the powder. As the moisture leaves, you will witness a final, beautiful transformation. The dark, brownish, wet sludge will slowly lighten in color, turning into the brilliant, unmistakable, radiant yellow of pure gold. You can gently break up any clumps with a glass rod to aid in the drying process, but be careful not to be too aggressive. The goal is a uniform, dry powder. The process is complete when you can see no more moisture and the powder flows freely like fine, glittering sand. To be absolutely certain it is dry, you can continue to heat it for a little while longer after it appears dry. Let the dish cool down completely to room temperature before moving on to the final step. Weighing hot objects is a classic chemistry mistake, as the heat creates air currents that can throw off a sensitive digital scale. Once cool, what you have before you is the final product. It is no longer scrap, no longer an alloy, no longer a wet sludge. It is a pile of nearly perfect, 99.99% pure gold, ready for its final accounting. This is the moment that quantifies your success. It is where the long, patient journey of science, preparation, and process is translated into a simple, tangible number. The weighing of the final product is the moment of truth. Before you begin, make sure your high-precision digital scale is on a perfectly level, stable surface, away from any drafts or vibrations. Turn it on and let it stabilize. Then, place a clean, empty weighing boat or a piece of weighing paper on the scale and press the tare, or 0 button. This subtracts the weight of the container, ensuring that the number you see will be the weight of the gold and nothing else. With a steady hand, carefully transfer your gleaming, dry gold powder from the evaporating dish onto the scale. You can use a soft, clean brush to sweep every last speck, ensuring nothing of value is left behind. As the powder piles up, watch the numbers on the digital display climb. This is, honestly, the culmination of your work, the direct measurement of the wealth you have created. The final number that settles on the screen is a powerful testament to the transformation that has occurred, from a pile of discarded scrap to a measured quantity of one of the purest substances on Earth. This final weight allows you to perform a critical calculation, your yield. By comparing the weight of your pure, refined gold to the initial weight of the scrap you started with, and accounting for its carat purity, you can determine the efficiency of your process. For example, if you started with 100 grams of 14 karat, which is 58.3% pure gold, you had 58.3 grams of gold to begin with. If your final pure gold powder weighs 57.5 grams, you have achieved an impressive recovery yield of over 98%. This analysis is what separates a hobbyist from a true refiner, providing valuable feedback to optimize your technique for future runs. Look at the pile of gold on your scale. It represents so much more than its monetary value. It represents knowledge, patience, and the successful application of science. It is a story of transformation, from chaos to order, from impurity to perfection. You started with scrap, followed a process, and created a tangible asset of verifiable purity. Every gram on that scale is a testament to the power of understanding the fundamental principles that govern our world. This is not just a weight, it is a victory. It is the final, undeniable proof of your success. The journey has brought us to a pile of beautiful, shimmering, 99.99% pure gold powder. This form, while pure, is delicate and difficult to handle. For storage, for admiration, and for the sheer satisfaction of completion, many refiners choose to take one final, dramatic step, melting the powder into a solid bar. This optional act is the ultimate consolidation, transforming the fine, dusty particles into a single dense and tangible ingot of pure wealth. It is a return to the element of fire, not for purification, but for unification. This final melt is a celebration, a moment of pyrotechnic beauty that crowns the entire intellectual process of electrolytic refining. To begin this fiery conclusion, the pure gold powder is carefully transferred into a high-quality ceramic or graphite crucible. It is essential to use a clean, dedicated crucible that has never been used for impure metals, as any residue could contaminate the final product and undo all our hard work. A small amount of flux, such as borax, is often sprinkled over the top of the powder. The flux serves multiple purposes. It helps to clean any remaining microscopic impurities, lowers the melting point slightly, and creates a protective molten layer over the gold, shielding it from oxygen and ensuring a smooth, glassy surface on the final bar. Now, the heat is applied. Using a powerful oxypropane or MEPPPC gas torch, the flame is directed onto the powder in the crucible. The heat must be intense and focused. You will watch as the edges of the powder begin to darken and then suddenly collapse inward, transforming from a solid into a liquid. The individual grains surrender their form and merge into a single glowing molten bead. The surface of this liquid gold dances and shimmers like a tiny captive sun, a mesmerizing sphere of pure liquid energy. It is a sight that has captivated humanity for millennia, a direct connection to the ancient origins of metallurgy. Once the entire mass of gold is completely molten and flows like water, it is ready for the pour. The crucible, glowing bright cherry red, is carefully lifted with tongs. The goal is to pour the liquid gold into a preheated graphite mold. Heating the mold is a critical step. Pouring hot liquid metal into a cold mold can cause it to splash violently or even fracture the mold. The pour must be quick, confident, and smooth, a single decisive action that guides the river of liquid gold into its final resting place, where it will cool and solidify into the iconic form of a gold bar. As the molten gold fills the graphite mold, its fiery orange glow begins to fade almost immediately. The surface solidifies first, the color shifting from bright orange to a dull red, and then to the familiar warm yellow of solid gold. This cooling process, while rapid, should not be rushed. Allowing the bar to cool slowly within the mold prevents stress fractures and ensures a solid, homogeneous ingot. This is a moment of anticipation, the final few minutes of waiting before the grand reveal. The heat radiates from the mold, the last vestiges of the energy required to give the gold its final, permanent shape. After a few minutes, when the bar is fully solid and has cooled enough to no longer be glowing, the mold can be carefully inverted. The gold bar, dense and heavy, will drop out with a satisfying and definitive thud. Due to the non-stick properties of graphite, it should release cleanly. What emerges is an object of immense beauty and significance. Its surface may still be coated with a thin, glassy layer of solidified borax flux, which can be easily removed by quenching the still warm bar in water, causing the flux to crack and flake off with a satisfying sizzle. What you now hold in your hand is the culmination of the entire journey. It is no longer scrap, no longer a chemical solution, no longer a delicate powder. It is a solid, substantial bar of 99.99% pure gold. Its weight feels significant, its density surprising. The surface gleams with a luster that no alloy can replicate. This is not just a piece of metal, it is a physical embodiment of knowledge, patience, and precision. It is a symbol of a successful transformation, a testament to the power of science to create order from chaos and to unlock profound value from the discarded and forgotten. This final solid form is the ultimate trophy. It is a bar of refined intelligence, a tangible asset created through a deep understanding of chemistry and electricity. It represents the end of one journey and the potential for countless others. Whether kept as a store of value, a piece of art, or a reminder of your own capability, this gold bar is more than its weight. It is the story of a transformation you commanded from start to finish. It is the proof that with the right knowledge, you can not only refine gold, but also transform your own potential. We began this journey with a simple, yet profound question. What if you could take discarded scrap and transform it into nearly perfect, 99.99% pure gold? We have now answered that question. We have walked the path from tarnished and forgotten objects to a gleaming, tangible asset of immense value. We have witnessed the quiet, elegant power of electrolysis as it commanded atoms to separate and reorganize, obeying the fundamental laws of chemistry and physics. But the true transformation, the most valuable refinement, is not what happened to the metal. It is what happens to our understanding. This journey was never just about making gold. It was about making sense of the world. This process has taught us that the most powerful forces are often the ones we cannot see. We did not use the brute force of a roaring furnace or the violent power of a hammer. Instead, we use the silent, invisible flow of electrons, guided by a precise understanding of electrochemical potential. We learned that true control comes not from overwhelming power, but from intelligent application. The ability to separate one element from another, atom by atom, is a testament to the fact that knowledge is the ultimate tool. It allows us to impose order on chaos, to extract purity from a complex mixture, and to create value where it was previously hidden. The gold bar that may now sit before you is more than a financial asset. It is a diploma. It is a certificate of completion for a deep and practical lesson in science. It represents patience, demonstrated during the slow, deliberate growth on the cathode. It represents precision, required for setting the exact voltage and preparing the electrolyte. And it represents respect for the potent chemicals and electrical forces that demand a safety-first mindset. The gold itself is a secondary reward. The primary reward is the empowerment that comes from knowing that you can manipulate the very building blocks of matter. This journey beyond the metal is a shift in perspective. You will never look at an old piece of jewelry or a discarded computer chip the same way again. You now see them not as junk, but as reservoirs of potential, waiting for the right process to unlock their hidden worth. This new vision is the core of the alchemist's modern dream. It is the understanding that with the right knowledge, the world is not a fixed and static place, but a dynamic system of materials and energies that we can learn to guide, shape, and transform to our will. The process of electrolytic refining serves as a powerful metaphor for the value of applied knowledge. In an age of endless information, it is easy to accumulate facts without ever translating them into action. This essay was designed not just for you to know, but for you to do. The real power was not in reading about anodes and cathodes. It was in the potential to actually build a cell, to prepare an electrolyte, and to witness the transformation with your own eyes. It is in the application of knowledge that true understanding is forged. The difference between knowing the path and walking the path is everything. This principle extends far beyond the realm of gold refining, the ability to take a complex scientific concept, break it down into manageable steps, and apply it to achieve a tangible result, is one of the most valuable skills one can possess. It is the foundation of all engineering, all technology, and all innovation. Whether you are building a circuit, writing a piece of code, or refining precious metals, the underlying process is the same. You learn the rules of a system, and then you use those rules to make something new. This is the engine of human progress. The knowledge you have gained is a form of personal sovereignty. It is the ability to create real, tangible value from raw materials using your intellect and skill. In a world where so much value is abstract and digital, the power to produce a physical asset of verifiable purity is a profound feeling. It is a connection to a long history of artisans, scientists, and engineers who have used their hands and their minds to shape the physical world. This is not a secret guarded by an elite few. It is a science, and its principles are open to anyone with the curiosity to learn and the discipline to apply them safely. Let this experience be a catalyst. Let it inspire you to look at other complex systems and ask, how does that work? Could I understand it? Could I do it? The confidence gained from successfully navigating the intricate steps of electrolytic refining can be applied to any field of study. It proves that with a methodical approach, a respect for safety, and a healthy dose of patience, no process is too mysterious to be understood. The power is not in the gold. It is in the realization that you have the capacity to learn, to apply, and to create. This essay is not an ending. It is an invitation. It is a doorway into a larger world of science, chemistry, and material transformation. The refining of gold is just one application of the principles of electrochemistry. The same fundamental forces can be used to purify other metals, to plate one metal onto another, or to etch intricate patterns onto a surface. The knowledge you have acquired is a key that unlocks countless other doors. The journey of discovery does not have to stop here. The world is full of hidden processes and untapped potential, waiting for a curious mind to explore them. We encourage you to keep learning. Dive deeper into the chemistry of the anode sludge to recover the silver and platinum group metals left behind. Explore other refining techniques, like the Miller process or fire assaying, to understand their strengths and weaknesses. Study the science of alloys to learn how different metals combine to create materials with unique properties. The more you learn, the more you will see the interconnectedness of science, and the more capable you will become. The pursuit of knowledge is a journey with no final destination. If this journey has opened your eyes to the power of applied science, we ask you to share that inspiration. Like this essay, share it with others who have a curious mind, and subscribe to continue your education. There is a universe of knowledge waiting to be explored, from the secrets of metallurgy to the frontiers of physics. Our goal is to continue providing the keys to unlock that knowledge, to demystify the complex, and to empower you to become not just a consumer of technology, but a creator and a master of it. Remember the central lesson of this entire process. Value is not inherent. It is created. It is created through intelligence, through process, and through the will to transform the ordinary into the extraordinary. You have now seen how science can turn scrap into treasure. You have learned that the most valuable asset you can ever possess is knowledge, because those who understand how the world works are the ones who have the power to change it. Keep learning. Keep building. Keep transforming.